This is Stat 512, Multiple Linear Regression Final Project Presentation by Eli McDermott, Neil Lunsavat, and Arna Maheshwari. The project examines the relationship between socioeconomic variables, environmental pollutants, and health vulnerabilities in Indiana. Using data from the CDC's Environmental Justice Index, we investigated the impact of socioeconomic status variables and environmental burden variables versus the health vulnerability variables. Multiple linear regression was the primary statistical method completed by diagnostic tests like the Brush-Pagan test for heteroscedasticity and the Shapiro-Wilk test for residual normality. Processes, methods, and transformations discussed in class were used to refine the model to make them most appropriate. Important findings on each topic will be highlighted later in the presentation. Environmental justice highlights the disproportionate exposure of marginalized communities to environmental pollutants and their heightened vulnerability to adverse health outcomes. Exposure to these vulnerabilities has been directly linked to chronic conditions, placing a significant burden on healthcare systems and reducing quality of life. Using Indiana-specific data allows us to analyze these disparities at the census tract level. By focusing on Indiana, we can provide actionable insights that are directly relevant to the local policymakers and public health officials. Ultimately, this project aims to bridge the gap between data and policy, ensuring that interventions are directed to the most affected areas, mitigating both health and environmental inequalities.
Thank you, Eli. Now I'll be presenting my research on how housing burden and minority status are linked to mental health prevalence. My primary question is, do these factors, either individually or through their interaction, significantly affect the prevalence of poor mental health in Indiana communities? In this study, I looked at housing burden, labeled as X1, which measures socioeconomic strain, and minority status, labeled as X2, which reflects demographic composition. My dependent variable Y is mental health prevalence, represented as a percentage. To guide this analysis, I developed two hypotheses. The null hypothesis states that neither housing burden, minority status, nor their interaction have any significant effect on mental health prevalence. The alternate hypothesis suggests that at least one of these factors does have a significant impact. With that framing in mind, let's look at how I approached building and evaluating my model. For this analysis, I built two models, a reduced model, which includes only the main effects of housing burden and minority status, and a full model, which includes their interaction term. Including the interaction term allows us to examine whether the combined effect of housing burden and minority status is significant. To validate the models, I ran diagnostic tests. First, the Brush-Pagan test indicated that the residuals had constant variance, so heteroscedasticity wasn't a concern. Second, I checked multicollinearity using variance inflation factors, or VIFs for short. Both housing burden and minority status had acceptable VIFs, but the interaction term was slightly higher, which is expected with interaction terms. Finally, the Shapiro-Wilk test showed some non-normality in the residuals, but the results are still robust enough for interpretation. When comparing the reduced and full models using an F-test, the full model was significantly better with an F-statistic of 18.28 and a p-value of 2.03 times 10 to the negative fifth. This told me that including the interaction term improved the model's ability to explain variations in mental health prevalence. Now, let's dive into regression results and what they tell us. Here, I'm showing the regression results for the full model. The equation predicts mental health prevalence as a function of housing burden, minority status, and their interaction. The coefficient tells us a lot. Housing burden has the strongest positive effect on mental health prevalence with a highly significant t-value of 18.236 and a p-value below 2 times 10 to the negative 16th. Minority status, on the other hand, has a small negative effect, but it's still significant. Finally, the interaction term has a t-value of 4.276 and a p-value of 2.03 times 10 to the negative fifth, which confirms that the combination of housing burden and minority status is a significant predictor. The model as a whole is highly significant within an F statistic of 407.8 and a p-value well below the standard threshold. These results strongly suggest that both individual and interactive effects are important, and they lead directly into testing my hypothesis. To test the hypothesis, I focused on the interaction term. The null hypothesis assumed that the interaction term has no significant effect on mental health prevalence, while the alternative hypothesis posited that it does. Using a test statistic of 4.276 compared to a critical value of approximately 1.96 at a 95% confidence level, I found that the test statistics exceeds the critical value. This means we reject the null hypothesis and conclude that the interaction effect is statistically significant. On the right, you can see a plot illustrating this. The different trends in mental health prevalence across levels of minority status show how the interaction shapes the outcome. For example, higher minority status tends to amplify the effect of housing burdens on mental health. These findings support the idea that housing burden and minority status don't just have independent effects, they also work together in important ways. Now let's transition to the limitations of the analysis. While these results are significant, there are a few limitations to keep in mind. First, there are data limitations. For example, minority status and mental health prevalence might not fully capture the complexities of the variables they present. Second, the model assumes linear relationships, which could oversimplify the reality of how these factors interact. Lastly, external factors such as access to healthcare, income inequality, and neighborhood infrastructure weren't included, and these might also play a role in explaining mental health prevalence. Acknowledging these limitations provide direction for future research, which I'll touch on in the next slide. To summarize, this analysis shows that both housing burden and minority status significantly affect mental health prevalence, and their interaction plays a critical role. These findings suggest that interventions focused on reducing housing burden could have varying impacts depending on the demographic composition of the community. Additionally, targeted mental health support in high burden, high minority areas could be especially effective. In the future, I'd like to expand this research by incorporating additional factors such as income and healthcare access, and by replicating the analysis in other states to enhance generalizability. Now I'm going to pass it off to Arna, who's going to go over the second research question.
Environmental pollutants like diesel particulate matter are well-documented contributors to health risks, including cancer. Similarly, minority status and poverty often correlate with socioeconomic inequities, influencing these risks. Our study bridges a gap in understanding their combined impact with a focus on Indiana communities. Our goal is to determine whether diesel particulate matter, minority status, and poverty significantly influence health vulnerability risk to cancer. To test this, we set up hypotheses to evaluate the relationship between these predictors and the response variable. Our response variable is the health vulnerability risk to cancer, as we can see on our slide here, while the explanatory variables tend to be diesel particulate matter, which is a continuous variable, minority status, which is a categorical variable, and poverty, again, a continuous variable. Our null hypothesis states there is no significant relationship between these predictors and our response variable, while the alternative hypothesis states that there is at least one predictor significantly impacting the health vulnerability risk to cancer. Step 1. Data and cleaning. We used the help of RStudio to remove all missing values from our data and landed with 1,505 observations about Indiana. Next step we did was address the issue of multicollinearity. Pairwise correlation and VIF diagnostics showed no significant correlation among predictors, as we can see in these images above, confirming that they are suitable for linear regression. Step 3, best subset selection. We used best subset selection to identify the most impactful predictors. We evaluated models using statistical metrics like PRESS, SPC, AIC, etc., which resulted in poverty getting dropped as an explanatory variable. This left us with diesel particulate matter and minority status emerging as the strongest predictors, supported by both statistical metrics and visual validation through added variable plots, as we can see in the images here. Step 4, influential points and remedies. Now that we are left with the only best suited variables, we identify influential points, for which we used Cook's distance and DF beta's metrics. The presence of large circles in the plot is a key indicator that the data points identified by the AV+ function are influential and should be remedied before proceeding with a hypothesis test. Therefore, I performed robust regression and bootstrapping to remedy these issues. Robust regression reduced MSE from 0.1953 to 0.1904, while bootstrapping ensured stability of coefficients. Step 5, hypothesis testing. The null hypothesis states that neither diesel particulate matter nor minority status has a significant relationship with health vulnerability risk to cancer, while the alternative hypothesis asserts that at least one predictor impacts the health vulnerability risk of cancer. We used bootstrapping to compute confidence intervals for the coefficients. The results, as we can see, showed that the confidence intervals for both predictors beta 1 and beta 2 excluded 0. This allowed us to reject the null hypothesis, confirming that both predictors are significantly impacting our response variable. This led us to have the final model equation, which included beta 1, beta 2 both as predictors, while beta 0 acted as the intercept. Step 6, model validation and limitations. Using tenfold cross-validation, we validated the model's performance and understood the limitations with our statistical inference. Given the moderately low R-squared value, which is 0.296, the model displays some bias in explaining the variance in cancer vulnerability. This suggests that while the predictors are significantly impacting the health vulnerability risk of cancer, other factors may contribute to the variability. However, the low RMSE and standard deviations indicate a low likelihood of overfitting. This implies that the model will likely have similar predictive power when applied to new data. In conclusion, our study revealed diesel particulate matter and minority status are significant contributors to cancer vulnerability. These findings underscore the importance of targeted interventions to reduce air pollution and address socioeconomic disparities. While our model highlights critical predictors like minority status and diesel particulate matter, future research could include other variables to enhance the explanatory power of cancer vulnerability.
Question 3 focused on whether PM 2.5 and diesel particulate matter contribute equally to asthma vulnerabilities, or if one of the pollutant has more significant impact. This question is crucial because identifying the most impactful pollutants allows for targeted interventions and better informed regulatory policies. Understanding the relative contributions of these pollutants is particularly important in addressing health disparities that disproportionately affect marginalized communities. By prioritizing interventions where they are needed most, public health strategies can be more effective and equitable. I tested the null hypothesis that PM 2.5 and diesel particulate matter have equal effects on asthma vulnerability. This meant comparing the relative significance and coefficients of each variable using statistical modeling. Rejecting the null hypothesis would indicate that one pollutant has a more substantial effect, providing critical insights for environmental health initiatives. Ultimately, this research not only addresses academic questions, but also has real-world implications for improving community health and reducing environmental injustices. To analyze the data, I started with exploratory data analysis to understand the relationship between variables by creating a scatterplot matrix and correlation matrix to evaluate variable relationships. This initial step gave me a sense of how PM 2.5 and diesel particulate matter interact with asthma rates and with each other. For example, diesel particulate matter showed a stronger correlation with asthma vulnerability than PM 2.5, which had a weaker association. This helped inform the development of the initial multiple linear regression model. I also performed key diagnostic tests to evaluate the model's assumptions. Residual plots in the Brush-Pagan test revealed heterostaticity, while the Shapiro-Wilk test confirmed non-normality in the residuals. These issues, if left unaddressed, could lead to biased estimates and unreliable conclusions. To address these problems, I applied weighted least squares to mitigate heteroscedasticity and log transformed the response variable to stabilize residual variance and improve normality. Bootstrapping was also used to validate coefficient estimates, ensuring that the model's findings were robust and not overly sensitive to outliers or data quirks. In the initial model, both PM2.5 and diesel particulate matter were significant predictors of asthma vulnerability, but the diagnostics revealed substantial issues that warranted refinement. Weighted least squares address heteroscedasticity, improving the model's fit, while the log transformation corrected for residual non-normality, ensuring that the statistical results were both valid and interpretable. Diesel particulate matter consistently showed a stronger impact on asthma vulnerability than PM2.5. Specifically, in the final log transform model, diesel particulate matter had a beta value of 0.4429, indicating a significant positive effect on asthma rates. In contrast, PM2.5 had a beta value of negative 0.42231, showing a significant negative association. These results allowed us to reject the null hypothesis that the two pollutants are equally influential. Importantly, the stronger effect of diesel particulate matter suggests that reducing exposure to this pollutant should be a key focus for public health interventions. Also, PM2.5's negative association raises questions about unmeasured factors, such as potential confounders or interactions with socioeconomic variables. Nonetheless, the results provide a clear direction for prioritizing diesel particulate matter in future interventions. Based on the findings, diesel particulate matter plays a larger role in driving asthma vulnerability, making it a key target for public health efforts. By prioritizing interventions to reduce diesel particulate matter exposure, particularly in high-risk areas, we can potentially mitigate asthma rates and improve community health outcomes. However, PM2.5's negative association requires further exploration to understand its impact fully. The model's low R-squared value, which explained only 5.79% of the variance, also underscores the need to incorporate more variables to better capture the complexity of asthma vulnerability. This analysis bridges the gap between statistic modeling and real-world applications, emphasizing the importance of data-driven approaches to tackle public health challenges.